is going to talk about time-resolved photochemistry of organic solutes in aqueous microdroplets. Thank you.
Does this work?
If you press the down arrow, it goes.
Okay,
It changes slides.
okay, cool.
Okay, and then that should laser.
Hi, so yeah, my project's on time-resolved photochemistry of aqueous solvents in aqueous solutes in microdroplets. Just a bit of content, so I'm just going to go. I'm just going to go around, go over some background for my project, the aims and objectives of my project, some of the spectroscopy techniques we are employing, and some of the results we've gotten so far, and then some future work. So there are many different types of organic aerosols in the atmosphere. The two main come under primary organic aerosols and secondary organic aerosols. I'm looking at some chemicals involved in secondary organic aerosol formations. This one in the middle. Oh. Yeah. So, I'm looking at this one in the middle here, pyruvic acid. Its precursor is isoprene, which is a biological VOC, and it's involved in those formation of the secondary organic aerosols. Pyruvic acid is of interest to us because it is a environmentally dependent molecule. So depending on which environment it is, it will either, so for instance, in water, it decarboxylizes, and in an organic solvent, it reduces. And so we just want to try and understand what it does in an aqueous environment. So we're trying to employ some spectroscopy to see how it reacts with light. So here you've just got a bunch of different other pathways that we get with pyruvic acid, and this is in aqueous, but it's still relatively unknown how we get to these in photochemistry. So we're just trying to explore that using some new techniques. So the main aims of my project, my first one is using our ultra-fast photochemistry spectroscopy techniques to look at the alpha ketone, so pyruvic acid. And we had a look at some other molecules, but I won't be talking about them today. And then we're going to go from looking at bulk solutions into droplets by constructing a droplet levitation apparatus, which will couple with the spectrometer. We're sort of at this stage now, and then we're going to try and vary some experimental parameters in both the bulk and the droplet stages, and eventually see if there are any other spectroscopy techniques we can use with this setup as well. So pyruvic acid, the commercially available stuff isn't very pure, and when we were first doing some initial experiments, we were finding that actually we were getting some like cloudiness with our sample, and with the techniques we are using, this can often create a lot of noise in our data. So we had to distill it first so we can get some more pure sample, and you get like this crude mixture of dimers and oligomers, which then we can use in our experiments. So one of the first techniques we used was time correlated single photon count, and this is basically to measure the fluorescence lifetime of our sample. This may look very complicated, but essentially we're exciting with a UV excited wave pulse, and then collecting here photons over time. This is our sample, it's just in a cuvette, so we're just looking at bulk initially of pyruvic acid. So we're basically measuring photons coming out of our sample, and then we're able to form this histogram here. And from here, we're able to get a fluorescence lifetime. And this is useful because then we can assign this to our S1 to ground state decay, which will come into a bit later on. Another technique we've been using is transient absorption spectroscopy. So we basically pump our sample here, using UV light around 345 nanometers, about sunlight, and then we pump using a white light continuum, and we're able to see the time change of our molecule over femtoseconds, picoseconds, all the way up to milliseconds. So we're able to see how the molecule is excited and then relaxes over time, and that gives a specific profile to that molecule. Over here is our Harrick cell, and we use this basically to pump through our solvent so that we don't have it photoexcited and photo-bleached, otherwise we won't get a proper measurement. And this is where we were getting problems with the impurities getting stuck on the cap windows, and we were getting a lot of noise. So here are just some of our results when we were looking at concentration dependence. And as you can see, it's pretty similar throughout. You sort of see it grows up in time and sort of shifts slightly downfield. But this is fairly consistent for different concentrations. So there is no, we don't think in acetonitrile at least, there is any concentration dependence. Water is a different matter. I'm not going to talk about it in water at the moment because it's more complex and we're still waiting for computational data. But yeah, in acetonitrile, we're not seeing a concentration dependence. But we're able to extract several lifetime time constants from this. And this one is the one we fixed from earlier because we know that the S1 to ground state decay is your fluorescence. So yeah, we're able to get several time constants out of this so we can build a better picture of its photo mechanisms. And then again, we did some wavelength dependent measurements, and you can see there's a little bit of difference during these measurements, but overall it's fairly consistent. And again, we were able to get a more of a shorter time constants from this. So we're trying to build several different pictures of this whole photochemical mechanism. And these are just several of the proposed mechanisms we have. In the gas phase, it's fairly well known. It excites up into a T state and then comes back down. But in the aqueous solution, we are suggesting that there might be a T2 state. And how we get from this, we're just looking at waiting for computational data to support our theories. But we have some fairly recent data that suggests that we're on the right track. So we could possibly two mechanisms going from S1 to a T2 to a T1 state, or we're just seeing some S1 to T1. But again, we're waiting on some computational data. So here we have the LDB, the levitating droplet device. So we're basically able to stream a line of droplets. It can be two extremes. We can have some small, we can control the speed of the droplets, like here on the right, and then you can also have it just flowing out really fast. So we want sort of a middle state like this, so that we're able to align the droplets with our laser, so we're able to detect the emission. And these were provided by Tony, who's in our group postdoc. So yeah, we're able to, with the help of Tony, we've been able to synchronize a nanosecond laser with the droplet apparatus and get a reading from that. And you can see over here, we're able to detect some measurements from that. And this is it basically proving that we can move this on to our spectroscopy techniques. So yeah, we've now done some TCS-PC using the droplet apparatus, but we've been using dyes just to try and calibrate the system. So this is using coumarin 480, and we're able to get another fluorescence lifetime here, and then we can compare this to the actual droplets. So this is some droplets we've done, and if we plot on the same mono-exponential graph, we see a fairly similar picture to the bulk. But if we put it in a bi-exponential, which there is potential, we see a slightly different weighting, and we're not quite sure why this is yet. But again, we're hoping to use some more. We're hoping to employ some different molecules such as PA in the future to see if we see a similar picture. So just a quick summary of what we've done so far. For the fluorescent lifetime measurements, we've done in aqueous and organic bulk solutions. We've done some transient absorption measurements on aqueous and bulk solutions, so we've got data on that, and we've been able to synchronise the falling droplets with the TCSPC, and collecting TCSP data on pyruvic acid is next, and then hopefully moving on to transient absorption. And also, I'd just like to say, I've just started my, just finished my placement at Post through a policy placement application for UKRI, and I'd recommend anyone who wants to get involved in policy or anything to do with the application of science communication to just have a think about if they'd want to do the placement. This is one of the research papers we just published. And yeah, it's really good fun. So, and you get to hang around in Westminster. But yeah, thank you to the group, and thank you to Tony and my supervisors, Brian and Andrew.
What, any questions?
I've got a question. Thank you very much, Conlan. So thinking about your falling droplet or that instrument, when you're doing those measurements, is that a single droplet measurement, or are you illuminating multiple droplets within the bead?
Hoping single droplets, but yeah, multiple different droplets, not the same droplet being like constantly. It's a flowing stream, so
Okay,
yeah.
so it's flowing, but each event is that a single
Yeah,
droplet passing?
yeah, they're about 30 microns, so yeah, it's about
Brilliant, thank you.
Great. Because we started a bit late, I might move on to the next. Thank you. Thank you very much. Thank you very much.